Good afternoon, everyone. On behalf of Cal State LA's Civil Engineering Senior Design Group 1, the following presentation will be on our submission, the Cajalco Road Roller Compacted Concrete Dam Project. This project is prepared for our clients, a group of companies with mining operations in Southern California and throughout the globe. The initial problem posed to the entire group involves solving these clients' mining interests, long-term diminishing groundwater supply issue in unincorporated areas of Riverside County and the adjoining eastern side of the city of Corona. The task was to develop a new source of high-quality non-potable water. The main approach that we would take would be to propose a solution that would incorporate a storage and conveyance system for the necessary services while minimizing environmental impacts, along with not hindering the operation of any mining facility involved by having continuous operations throughout the construction process. The team would separate this project into two phases. The first phase would primarily consist of initial design along with the planning of potential methods, options, and locations to solve the problem. Phase 1 was conducted in fall 2020. Phase 2, during spring 2021, would be taking the client's choice and implementing a design that meets all of their needs. As stated, the project location would be on the eastern side of the city of Corona, south of the 91 freeway, and east of the 15 freeway, off of Cajalco Road. Ultimately, through conversations with the clients, the prospect of a dam would be the best option. For the first phase of this project, planning and recommendations involving a dam was therefore the primary objective. For initial conceptual design, understanding our objectives and the methodology were the main focus. During pre-design, understanding potential constraints that included geotechnical, hydrological, structural, and environmental was a point of emphasis. Preliminary design involved discovering the best locations, alignments, storage options, road placement, and dam types. Final design provided all the team's recommendations along with a cost analysis. As shown in the figures to the right, the final recommendations for Phase 1 included a dam, alignment 2, site 4, and above-ground cylindrical stainless steel tanks. After all the Phase 1 presentations were provided, each team was then tasked with a specific type of dam. For Phase 2, Team 1 was tasked with the planning of a roller compacted concrete, or RCC dam. The process for Phase 2 would include dam design, spillway and outlet works to the pump station, onto the storage tank and pipeline alignment, an access road, a ZIKA evaluation, and a cost estimation. Shown here is an overhead view with important locations involved with this project. To the west of the dam site location is the city of Corona, to the east is Lake Matthews, and just to the south is Cajalco Road. If we zoom into this project location, various structures for this project are indicated. This location will be referenced throughout the presentation when discussing each of these individual structures. Before each of the project objectives, a project outline with the highlighted section will be shown. First, we will start with dam design.
Now we will present our proposal for the dam.
Project Team 1 was tasked to design an RCC dam. As shown in the slide, the dam is located south of Eagle Canyon Road, which meets the client's requirements. In addition, our design includes a permanent access road to the dam connecting the Eagle Canyon Road, which will further be explained by my colleagues. RCC dams are constructed lift by lift by cranes in successive layers, resulting in a slope that resembles a staircase as shown in the figure on the upper right-hand side. When constructing RCC dams, the demand for man-hours is less compared to conventional concrete dams due to the usage of machines for compacting and spreading the concrete as shown in the picture on the lower right-hand side. Bulldozers are the general equipment that is used for spreading RCC. An uncompacted lift gives the bulldozers the ability to work on the surface without damaging it. When the RCC has been placed and compacted, continuous curing is important just as for conventional concrete. The most crucial part of construction is that the RCC is transported, placed, spread, and compacted as rapidly as possible. The time from the start of the mixing to after it has been compacted should not exceed the initial time set of the RCC mixture. However, this time can be adjusted depending on the weather conditions. For warmer weather, the time should be reduced, while for cooler weather, the time can be extended. Compared to when constructing a conventional concrete dam, RCC dams differ in the aspects of the layout, planning, and equipment. A temporary dirt access road can also be created to further access the dam or used as a laydown area where material and machinery can be kept when construction is going on. The main reasons for designing RCC dams are the economy, the speed of construction, and the positive environmental effect due to less cement use. RCC dams are made of a composite construction material with no slump consistency and its unhardened state. This drier type of concrete usually consists of sand, cement, water, and mostly aggregates. Aggregates that are used for RCC mixtures can be found on the construction site, or it can be transported from an aggregate producer. Huge stockpiles of aggregates are necessary for an RCC dam construction and before starting the RCC work because the aggregate production capability might be exceeded by the usage rate of the aggregate during the placement of the RCC.
Through the United States Geological Survey, various faults surrounding our site location are the San Jacinto, San Andreas, and Elsinore faults. All of the major fault lines are marked in red on the map. These faults could cause the most damage to our dam due to their locations and fault activity. Out of the three faults, the Elsinore fault governs our design due to their proximity. The geotechnical report for the Lake Matthews outlet facilities prepared for the Metropolitan Water District of Southern California was used to characterize the subsurface geological profile since the site investigation is located 2.6 miles away from the proposed site location, making it a good estimation of the geological conditions at site. Most of the material found is granite, followed by diorite, with the marginal percentage of other materials. The peak ground acceleration, as depicted to the right in the design acceleration response spectrum, is 0.864, determined in accordance with ASCE 7 through 16. MCER is the maximum considered earthquake within the response spectrum. The structure is categorized as a risk category 2 and site class B as determined from the geotechnical report. Risk category 2 classifies the structure as non-essential compared to the other three risk category structures marked as essential, such as hospitals and schools. It presents a minor hazard to life if failure happens to the structure. Site class B means that the soil identified underneath the project site is mostly rock composition, as previously mentioned being granite and diorite.
A task we accomplished in the design phase is using the Rupa method to calculate the water demand based on inflow measurements from the watershed. In the figure, we have the cumulative inflow versus demand curves labeled. The biggest divergence from the cumulative inflow with respect to the mining interest demand was 160 million gallons of water. The 160 million gallons demand was used to calculate the capacity of the dam and determine the water depth height of 56 feet for the dam.
The freeboard is the vertical distance from the surface of the water in the reservoir to the crest of the dam, and its purpose is to prevent overtopping caused by large waves that are produced by wind forces. Some parameters of our design include the previously mentioned 56-foot reservoir depth, as well as a wind speed of 110 miles per hour and a wind fetch of 1 mile. We used those parameters to solve for the setup, wave height, and run-up. We then took the summation of the setup, run-up, and the required safety height to get a freeboard height of about 8 feet, as you can see from the image to the right.
The forces acting on the dam are the external water pressure, the seismic forces, and the uplift forces due to the penetration of the water into the porous material at the dam's base. The resistance mechanism is constituted by the self-weight of the dam and the base friction. Based on the reservoir water demand from natural sources, the height of the reservoir's water level is 56 feet with a freeboard of 8 feet, making the total height of the dam 64 feet. From height 57 to 64 feet, the forces acting on the dam are the self-weight, friction force, horizontal and vertical seismic force because of the freeboard. From the base to height of 56 feet, the forces acting on the dam include all the mentioned forces as well as the hydrostatic, hydrodynamic, and uplift forces.
With the acting forces of the RCC dam established, static and pseudostatic stability analyses were performed to determine the most plausible cross-section for the dam. To determine if the dam is stable against sliding and overturning under the loading conditions by calculating its factors of safety. In accordance with design standards by the U.S. Army Corps of Engineers, the safety factors must equal or exceed 1.5 under the static analysis, which does not include earthquake forces. Furthermore, the safety factors must equal or exceed 1.1 under the pseudostatic analysis, which does include earthquake forces. Stability of the dam was calculated through an iterative process for the dimensions of the dam's crest and base, as well as the slope of the lifts on both sides. Dimensions as well as the calculated forces were then plugged into both equations for the factors of safety as shown on the left. A stability analysis in which the stabilizing force is provided solely by the weight of the dam was performed, and the resulting factors of safety demonstrated that the dam's weight was sufficient to maintain stability within desirable dimensions. Under static forces, the factors of safety resulted to 2.43 against sliding and 3.82 against overturning. Under pseudostatic forces, the factors of safety resulted to 1.57 against sliding and 3.72 against overturning.
As explained in the previous slides, considering the acting forces on the RCC dam structure, as well as analyzing the stability necessary to withhold these forces, we were able to determine the dimensions of the dam as shown in the slide. A wider dimension for the dam is expensive since it uses more concrete material. However, it will have a higher overall stability. For a smaller dimensional width of concrete, the dam will be inexpensive, but will compromise the stability. However, our proposed design fulfills both criteria of being soundly stable and economically efficient. Now, my colleagues will go over the spillway.
In this section of the presentation, we'll be presenting the spillway design. After presenting the client with different spillway alternatives, a true spillway was selected. A true spillway is an open channel constructed on a slope with water flowing from upstream to downstream. This type of spillway directs water into the adjoining discharge area without a control gate. This ensures that the water is safely discharged in the event of excess runoff coming from the watershed. Looking at this image, you can see where the spillway is located within the entire project. Specifically, the spillway is in the center of the downstream face of the dam, with the flow of water represented by the yellow arrow. The following is an overview of the spillway's main dimensions. These dimensions were determined while evaluating the hydraulic conditions along the spillway. On the image to the right, you can see how the hydraulic conditions impacted the design of the retaining wall. We will further discuss our findings in the following slides.
To start our spillway design, we needed to determine the maximum discharge rate we should expect for Cajalco Creek. In our research, we found nearby precipitation data from a gauge point taken for Temescal Creek, which had a maximum discharge of about 6,000 cubic feet per second. Riverside County's flood control website stated that Cajalco Creek would receive about half of this watershed discharge. Therefore, we used 3,000 cubic feet per second for our calculations. First, we will look at calculations at the crest of the spillway. Here, we use the max discharge and a control width to evaluate the water's critical flow, critical depth, and critical velocity. Part of the design criteria was to keep the water's critical depth below 3 feet and the critical velocity under 10 feet per second. Through an iterative process, we found that the optimal dimension to meet this design criteria was a channel width of 105 feet, which would be used for the entire length of the spillway.
Next, we will look at the calculations at the middle of the spillway. Here, we first used Manning's equation to calculate the section factor and the water depth that corresponds to that section factor. Then, we used the water depth to determine the water's velocity, Froude number, and energy along the middle of the spillway before the hydraulic jump. Now, we will look at the calculations at the hydraulic jump. A hydraulic jump is an abrupt rise in a liquid surface when transitioning from a higher velocity to a lower velocity discharge zone. We first used the conjugate equation to calculate the depth of the water at the hydraulic jump. This allowed us to determine the water's velocity, Froude number, and energy at the hydraulic jump. We also determined that we would have about 46.23 feet of energy that needs to be dissipated.
We propose constructing a sealing basin at the base of the spillway as a way of dissipating the 46 feet of energy from the hydraulic jump. A Type 3 sealing basin is recommended for conditions where the Froude number is greater than 4.5 and the incoming velocity is less than or equal to 60 feet per second. Our calculated values indicate the need for this type of sealing basin. We will take a closer look at some of the details of our design in the following slide. We started our sealing basin design by determining some parameters and formulas that pertain to our water's characteristics before and after the hydraulic jump. This allowed us to calculate the dimensions for the baffle blocks and the chute blocks, which can be seen in details A and B. We also determined the length of the sealing basin, which is about 29 feet.
Here, we take another look at the water flow profile, which was constructed from the water depth along the spillway. At the crest, the normal depth is equal to the critical depth. In the middle section, Y1 is less than the critical depth. And at the hydraulic jump, Y2 is greater than the critical depth. This image shows two possible hydraulic jumps that could occur near the bottom of the spillway. Now we will look at the calculations for designing the channel retaining wall. We use the water's depth and velocity at the crest of the spillway, middle, and hydraulic jump to determine the height of the freeboard and retaining wall at each of these locations. At the crest, the retaining wall is 6 feet. Then at the middle, it decreases to 4 feet. Then it increases to 20 feet to accommodate for a hydraulic jump that could occur near the bottom of the spillway. And now we would discuss the outlet works.
In this section of the presentation, we will be presenting our proposed design for the outlet works. The following image shows the outlet work design consisting of an incline intake structure and access road to the intake structure connecting to Eagle Canyon Road, and one emergency discharge pipe connecting to the intake structure. The location of the incline structure is located 310 feet upstream of our proposed RCC dam. A rectangular incline structure was selected because it is ideal for low-level head reservoirs with large discharges and has easy constructability. The guidelines used for design were the Army Corps of Engineers Structural Design of Outlet Works and the American Concrete Institute codes. The image on the right represents our final design of our incline structure. The intake structure takes in water from the reservoir through orifices located on the tower. Once water begins to be drawn in, it is diverted away through an outlet pipe located at the tower base. The blue circles represent orifices, and the green circle represents the discharge pipe. The incline length of the structure is 263 feet, with shear keys on the bottom of the incline section to prevent sliding. The top of the structure will be at an elevation of 82 feet from the ground. The dimensions of the intake structure are shown on the image to the left. The following slides will go into more detail explaining how we came up with our design.
One major component to the intake structure is the emergency drawdown requirements if the dam were to experience substantial damage. The California Division of Safety of Dams outlines the minimum time requirement based on the volume contained by the reservoir. From our client's needs, we were able to approximate our volume to be 162 million gallons. So this reservoir is required to empty the first 50% of its volume between 7 and 10 days, and the second 50% of its volume between 20 and 30 days. From that, we can calculate the minimum required volumetric flow rate over a 24-hour period. The table shown lists the final flow rates with the 10-day drawdown period governing. With our flow rate, we're able to size our outlet pipe and size the tower orifices. Using the Design of Small Dams manual, our pipe was sized to be 1.5 feet in diameter, but we increased this to 3 feet to allow someone to enter the pipe for maintenance. We chose to use ductile iron due to its strength and its low cost. Using the American Waterworks Association manual, M41, we determined a minimum pipe thickness to be 0.31 inches using internal pressure. The image shown is a profile view of the incline structure. To ensure that we can draw water at variable water levels, we placed alternating orifices on both sides of the inclined structure, each increasing in elevation of 5 feet. Our outlet pipe is connected at the base of the structure. Due to the low velocity in our outlet pipe, it will need to be flushed regularly to remove sediments.
A slope stability analysis of the existing ground surface at the incline intake structure location was conducted using GeoStudio's SlopeW software. In the absence of a geotechnical characterization at the site, the subsurface soil profile was assumed to be homogeneous, cohesionless soil with a unit weight of 120 pounds per cubic foot and a friction angle of 32 degrees. A static slope stability analysis was performed using Bishop's method. The resulting factor of safety against slope stability failure is 1.4, as shown in the slide, which does not meet the requirements of a minimum factor of safety of 1.5 in accordance with the Federal Highway Administration. Under the same geological parameters, a slope with a 37% grade is proposed as shown in the profile. The resulting factor of safety against slope stability failure is 1.7, as shown in the slide, which meets the requirements of a minimum factor of safety of 1.5 in accordance with Federal Highway Administration. The cross-section of the proposed trench to be dug for the construction of the incline intake structure is shown in the upper left-hand corner. And only half of the infrastructure will be below grade, as shown by the gap between the design profile and the existing ground profile.
Since the structure is on an 18-degree incline, sliding is an immediate concern. Using a dynamic seismic model, a stability analysis was conducted in order to determine the sliding forces and sliding resistance forces. The sliding forces, those in red, and the sliding resistance forces, those in green, were used to determine the dimensions for shear keys necessary to stop sliding. Having completed the stability analysis, 21 shear keys were placed underneath the incline length with the following dimensions and intervals in the current slide. With a sliding factor of safety of 2.01 above the 1.1 requirement, the shear keys stopped sliding for the structure. Due to passive earth forces acting along the side of the shear key, reinforcement was needed to resist the moment caused by these forces acting along the shear key. Using AC load combinations, the ultimate moment was calculated by taking the moment above the central shear key using the resultant seismic and hydrostatic forces. Using ASA 318 codes, the area steel necessary is 2 number 14 bundled bars with 3-inch cover and a center distance of 6 inches.
Establishing the alignment of the intake structure governed the alignment of the discharge pipeline. The discharge pipe is to be connected at the base of the intake structure. After analyzing the site, it is recommended to bore through the side of the hill slope to the other side of the RCC dam. The image depicts a conceptual illustration of this idea. The pipe is to slope down from the intake to the pump station at a 6% slope. It will approximately span 450 feet. As discussed before, the alignment of the intake structure governed the alignment of the discharge pipeline and including the access road to the intake structure. This is a profile of the road to the intake structure compared to the existing ground. A 16% slope was maintained with minimal earthwork needed. The road spans 753 feet from Eagle Canyon Road to the finished floor of the intake structure. From all alignments, a 3D surface was created to analyze the interaction between the existing ground and the proposed elements. It is estimated to cut 10,128 cubic yards and fill 4,473 cubic yards. An excess of 5,655 cubic yards of earth will be exported from the inclined intake structure elements, such as trench, pipeline, and access road.
Next, we will be talking about the pump station. The purpose of the pump station is to house the necessary pumps that are being used to overcome any adverse forces taking place in the water flow process. These pumps will also act as the buffer to ensure that there is a constant reserve of water availability in the storage tanks and to maintain the desired supply capacity required by the mining interests. As shown in the figure to the right, the pump station will be located below the dam with the distance from the inlet water tower to be 470 feet and being approximately 2,800 feet to the storage tanks. In order to calculate the required horse pump power, we use two equations. The first equation is the energy equation. This was used to find our pump's head loss. The second equation was used for calculating horsepower. This equation utilizes the pump head loss calculated from the energy equation to find our required amount of horsepower for our pump.
Based off the neat flow demand of 1.8 million gallons per day, We use the energy equation to calculate for our pump head loss. Using the equation, we get a pump head of 300 feet. Using this pump head loss, we then solve for our required horsepower needed, with 505 horsepower being calculated. For this pump station, there will be 2 pumps, with one being online and one being a backup. They are required to be operational for 9 hours daily from 8 a.m. to 5 p.m. For this reason, our team recommendation will be 2 600 horsepower centrifugal pumps housed in a 10-foot by 15-foot concrete structure.
Good evening. I will be discussing the water tank and connecting pipeline. I will begin with the introduction of the pipeline alignment. The pipeline will begin just due south of the incline tower at the pump station, where we will tap into the emergency discharge pipeline using a uniform 1.5-foot diameter ductile iron pipe with a thickness of 0.26 inches to deliver water to the water tank. The total length of alignment is approximately 2,700 feet long and experiences an elevation gain of 220 feet from the pump station to the water tank. The alignment will consist of 8 bends, all of which will be 45 degrees, allowing for minimal head loss within the pipeline. Since the alignment will intersect the access road, the pipeline will be installed 4 feet underground to ensure feasibility, as well as to keep the pipe from erosion due to weathering over the years. The image shown is the profile of the alignment. The average slope consists of an 8% incline. The installation process of the pipeline will require a total cut of approximately 9,000 cubic yards of earth to be removed and then filled back in after the installation of the pipeline. Overall, the average length, slope, and total cost of the pipeline was determined to be most effective and efficient alignment compared to our alternative alignments.
In this slide, we will discuss the energy flow of the pipeline system. Based on the client's daily water demand and firefighting requirements, which will be covered in further detail in upcoming slides, a constant water flow rate of 14.85 cubic feet per second was determined and applied throughout the pipeline system. As shown, each of the 2 pipelines represents a different diameter and velocity, while maintaining the constant flow rate. D1 represents the diameter of the pipeline connected from the reservoir at the intake tower to the location of the pump. This was set as 3 feet. In this case, the corresponding velocity is V1 at a value of 2.1 feet per second. The diameter D2 represents the remainder of the pipeline system, which continues from the pump and connects to the other end at the storage tank. This was set as 1.5 feet. The corresponding velocity of this pipe is shown as V2 at a value of 8.41 feet per second. Essentially, an energy equation was used to calculate the pump head while pumping from the lowest water level of the reservoir. This would be the governing scenario for pumping, so that any amount of water may be collected and stored in the tanks. Head losses and proper elevations of all points of the pipes were accounted for in the process. Finally, it should be noted that the 3-foot diameter pipe has much smaller velocity than the 1.5-foot diameter pipe due to its larger size for purposes of maintenance work.
Now we're going to be introducing the water storage tank specifications. These tanks will be located northwest of the reservoir near Eagle Canyon and will be acting as buffers for the dam located between Eagle Canyon Road and Cajalco Road, and are designed to meet a minimum storage capacity based on the demand set by the clients, the hours of operation the tanks will be in use, water storage should operations go past regular business hours, and the minimum firefighting requirement in Riverside County for rural areas intended for fire department use in case of an emergency. Using the same approach as the Ripple method, the daily carryover storage volume was determined by finding the maximum divergence between the outflow of water over a 12-hour working period and the inflow of water over a 9-hour pumping period, resulting in the carryover volume being 450,000 gallons. After incorporating all factors into our design process, it was determined that our project would result in a dual storage tank system where each tank will have a capacity of about 1.8 million gallons.
We will now be discussing the tank capacity calculations. As mentioned previously, we have a daily carryover storage of 450,000 gallons of water. In addition to this water, we also include the firefighting requirements for the city of Riverside to get a total storage capacity. To solve for the firefighting required water, we use the equation shown on the slide. The firefighting requirement was found to be 3,140,000 gallons. By adding up both the daily carryover storage and firefighting requirement, we get a final capacity to be about 3.6 million gallons.
As mentioned previously, the total capacity the water tanks will need to hold is 3.6 million gallons of water, and each tank will hold a capacity of 1.8 million gallons. After analyzing the calculations, we determined that the best approach for our tanks to efficiently hold this capacity is to design two identical tanks. By designing two tanks, it will be more cost efficient and reasonable in comparison to one larger tank or several smaller tanks when it comes to maintenance or cleaning. Each tank will have the following dimensions: a height of 34 feet, allowing 4 feet of freeboard, a 100-foot diameter, and a 20-foot road to sit between the tanks and allow access for maintenance workers.
I will now be introducing the access road design to the dam. The access road to the dam will be focusing on Road 1, which is located along Eagle Canyon Road. It is a single-lane road with a span of 671 feet, designed for maintenance crews to have direct access to the dam after completion phase. This is a simulation of our final road design. During the design process, our goal was to design a road considering cost efficiency, earthwork, and materials required. These factors were considered led our team to implement a retaining wall with a max vertical height of 30 feet that will span 410 feet left of the road, reducing the overall amount of earthwork needed. Implementing a stable retaining wall will prevent any possible soil failures as well as maintain the height of the soil.
Our design includes a 671-foot road west of the proposed RCC dam. The road will consist of a 12-foot wide lane with 2-foot wide shoulders on each side. We were also asked to design a drainage system to collect and redirect any water source away from our access road. Now, if we look at the diagram, moving from left to right, the entry of the road will start at Eagle Canyon Road. About 1/3 of the way, we will have our first turnout highlighted in blue on the right-hand side of the road. After passing our first turnout is where the start of the retaining wall will be placed on the left-hand side of the road. The design of the retaining wall will be discussed later on in the presentation. About 2/3 of the way down the road is where our second turnout will be located on the left-hand side, highlighted in green. Each turnout will be 6 feet wide to allow vehicles to pull over and let other vehicles pass through. Finally, the road will be ending at the top of the RCC dam location. The end of the road will include a turnaround area highlighted in red with a 40-foot radius to allow vehicles to safely make a U-turn and head back up to Eagle Canyon Road. Now, if you look at the graph, the blue line represents a side profile of the road moving from left to right. The starting elevation is at 977 feet right off of Eagle Canyon Road and will end at an elevation of 895 feet, which is the exact elevation of the top of the dam. We were able to design the shortest access to the dam from Eagle Canyon Road without exceeding 16% slope.
Access road design solutions and why we chose them. We begin by developing the roadway alignment that connects Eagle Canyon Road to meet the top of the RCC dam. Using the Caltrans Highway Design Manual and topographic analysis, a significant slope alongside the hillside terrain spawns safety and cost issues. These issues were mitigated by developing a road design with minimal distance and acceptable cut and fill located east of RCC Dam at the curvature of the Eagle Canyon Road. Given the road design parameters, our turnouts and turnarounds are strategically placed to meet vehicle standards. This access road is mainly used for maintenance and possesses a low traffic volume, so we went with the asphalt flexible pavement design. The asphalt design consists of a layering of 4 inches asphalt and an aggregate base of 6 inches. For our drainage system, we're ultimately relying on the slope of the road. A 3/4 of a foot curb and grading to outflow location will guide the runoff straight to the V-shaped concrete drainage channel. The channel consists of 12 inches in height, a top length of 24 inches, downslope distribution south of the RCC dam.
We built the surface of the existing ground along with the surface of the road corridor in Civil 3D. With those, we were able to calculate the total earthwork required for the road construction. As shown on the graph, we plotted the proposed alignment shown in blue against the existing ground shown in red. This graph shows that we propose a net total earthwork of 11,932 cubic yards. This is designed with the retaining wall because it would be more cost effective than without a wall. Without a wall, the net total earthwork would be 49,447 cubic yards. So the wall reduces the total earthwork by 37,515 cubic yards.
Now I will be going over the retaining wall design. As previously mentioned, the goal was to reduce the total amount of cut required for Road 1, the road to the dam. So we implemented a retaining wall which reduced our overall amount of soil excavation to 11,900 cubic yards. For this road, we will have a total of 3 different size retaining walls. They have a total span of 410 feet, which will be going alongside the road at the edge of the 2-foot shoulder on the left side. We began designing our retaining walls by taking into consideration the soil parameters such as the passive and active soil pressure coefficients, soil density, allowable bearing pressure, and angle of friction. We checked for safety against sliding, overturning, maximum and minimum soil pressures, bearing capacity failure, and shear at the stem, toe, and heel. As you can see on the image on the right, we required a 20-foot wall, 25-foot wall, and 30-foot wall as the soil height varies along the length of the road. Each wall was placed accordingly depending on the height of our access road compared to the height of the existing ground. Here on the left, you can see a general cross-section of what each retaining wall will look like along the road. It will be a cantilevered concrete wall, and it will have reinforcement at the stem, toe, and heel, placed where the walls are prone to failure. The walls will also have a 6-inch perforated pipe with geofabric wrap and a 12-inch backfill for drainage of the soil. We also included weep holes to minimize the possibility of excess pressure buildup. The wall stem thicknesses will range from 2 to 3 feet, and the foundations will be 15 to 30 feet in length and 2 to 4 feet in thickness depending on the height of the wall.
We would now be moving on to the ZIKA evaluation. The air quality would be impacted due to the combustion from vehicles and heavy machinery throughout the whole construction phase. Particulate matter would also impact the air due to the constant moving on site. The mitigation measures are to use low emission equipment that meet Tier 4 emission standards, minimize idling for heavy machinery, and minimize the dust by utilizing equipment such as water suppression and wind fencing. For biological resources, the fauna and flora of the project site is similar to the Lake Matthews Reserve. The reserve is known to be an important bird resting area and feeding site during winter. Also, the Stephen's kangaroo rat is a threatened species being protected at the reserve. The mitigation measures for the biological resource is to have a qualified biologist to conduct a pre-construction survey if construction and vegetation removal is proposed between February 1st and August 21st. Any active nesting site shall be avoided until adults and youngs are no longer present on site. As for the other animals, such as the Stephen's kangaroo rat, they will be captured and relocated.
Perhaps the most significant environmental impact is the hydrological impact. Since the dam will create a reservoir by capturing rainfall water and creek flow water, the natural flow of Cajalco Creek will be severely reduced at the base. This in turn also reduces the amount of water entering the Temescal Wash, which connects to Cajalco Creek. In order to mitigate this, we released water from the dam based on how much water was estimated to originally flow prior to the dam being implemented and rainfall patterns from previous years. The source of this water will actually be transported through the outtake pipe and the intake structure. During the wet months, November to May, approximately 44,000 gallons per month will be released. During the dry months, June to October, approximately 353,000 gallons of water will be released per month. The goal is to maintain a similar flow and maintain a healthy watershed.
For land use impact, the proposed project would be in the direct use of physical land in between the Eagle Canyon Road and Cajalco Road. The land use will cover the area in Cajalco Creek and will be used to create the storage dam. We will conduct biological surveys, and the contractor will be restricted to the areas that have been cleared for construction only.
Noise pollution during the construction will occur in the site area due to heavy equipment usage and transportation. The noise pollution is inevitable during the construction phase. The area is away from residential areas, so this may not be a concern, but if needed, design measures such as noise barriers, curtains, or shields will be included. Tribal cultural resources. There are 2 Native American reservations that have ties to the land. These are the Soboba and Pechanga reserves. They are 2 groups from the band of the Louisiano Indians that used to live in the surrounding areas of Lake Matthews. Mitigation. The people currently have access to these lands and should not be deterred from entering the Mockingbird Canyon site for their spiritual and religious practices. Archaeological Resources Protection Act of 1979 protects these lands. Monitors will be on site during the entire process in case any artifacts are to be found.
Using the innovation sustainability guidelines, our project was able to significantly improve its sustainability prospects. The measures used to increase sustainability include using recycled material, managing air and sound pollution during construction, preventing flooding through dam reinforcement, and maintaining a healthy hydrological cycle of Cajalco Creek via water release.
Cost estimate. We are working with the Class 5 cost estimate. According to the Association for the Advancement of Cost Engineering, our range of accuracy at this level is 50% below to 100% above the actual construction cost. Now, construction costs can vary from these estimates because there are many uncontrollable factors, such as market conditions, change orders, legalities. Our expected accuracy is from 0 to 2% of the design, as you can see in the chart.
The chart is a breakdown of the Class 5 estimate. The dam, 33% of the total cost, would cost $25 million. The pump station, 4% of the total cost, would cost $3 million. The intake structure, 3% of the total cost, would cost $2 million. With a design and environmental cost of 15% each and a contingency of 30% of the building cost added to the total, it comes out to be $78 million.
Our final section of this presentation will be the summary. As stated initially, Team 1's objective for this project was to develop a new source of high-quality non-potable water by way of a roller compacted concrete dam. The team's strategy for the development of a roller compacted concrete dam was to take a comprehensive approach in understanding all the necessary obstacles that would potentially occur with a project this size. Using the water per day requirement, calculating and presenting plans for the construction of the dam in our planned location was executed. Developing all the ancillary necessities and structures associated would then take place after those calculations were accomplished. As discussed throughout this presentation, these included the dam support structures such as a chute spillway, intake tower, water storage tanks, pump station, pipelines, and access roads. A required CEQA and cost analysis were also accomplished. Throughout this entire process, it became evident that a roller compacted concrete would be an ideal option for the construction of a potential dam in this area. The inexpensive costs compared to conventional concrete show why RCC dams have constantly gained acknowledgement when building new dams. For these reasons, this would make our Cajalco Road RCC dam option an excellent choice. Thank you for your time. This concludes our presentation.